So in this lesson we're going to have a look at pedigree charts. Here is an example of a pedigree chart. It essentially is just showing how specific traits are passed on from generation to generation. In this case you can see there are 1, 2, 3, 4 generations. We're going to have a look at 3 different examples that you may get in an exam. In the first example you'll be told in the question that the disease is recessive. In the second example, you'll be told in the question that the disease is dominant. And in the third example, you are not told whether it's dominant or recessive, but you have to figure it out yourself and give a reason why. So the first example, recessive disease, for example, cystic fibrosis. So at the top here, we have the parents. Both parents are unaffected. Then in the second generation, their kids, they have 4 kids, and one of those kids marries a person, and they have 2 kids that make up the third generation. Over here on the right, I'll draw your attention to this box here, and this is a key to what those things in the chart mean. So if it's a circle, it's a female. If it's a square, it's a male. If it's not filled in, it's a female. It's unaffected, and if it is filled in, they are affected, i.e. they have the disease. So in an exam, you may get asked to figure out what the genotype of a person is. So for example, let's try and figure out what person A is. As with any other genetic problems, we have to first start off by assigning letters to unaffected and affected alleles. So let's say that capital B is unaffected because unaffected is dominant, and then lowercase b is going to be affected, or let's just shorthand put CF for cystic fibrosis in this example. Now there are 3 possible genotypes. You can either have 2 big B's, a big B and a little b. These will both result in an unaffected phenotype. The third possible genotype that we can have are 2 small b's, and that would mean they have the disease or they have cystic fibrosis. So all the people on this chart can only be one of these 3 genotypes. Getting back to person A is actually pretty easy to figure out what they are because they are affected, so they have to have the genotype small b, small b. Similarly, their son also has to have 2 small b's because he is also affected. Let's say then we have to figure out what person B is. They could either potentially have big B, or big B, little b because they are unaffected. However, because they have a child who is affected, they have to have at least 1 small b. The other one has to be a big B because they are unaffected. So person B is actually heterozygous, or they are a carrier. By that same reasoning, the grandparents also have to be big B, little b because they have a child A who has the disease. Sometimes in a question you may actually have a pedigree that looks a bit different. You may have something that looks like this, or like this, kind of half filled in, and it's not a person winking. What this also can show in a question is that the person, this female, is a carrier. But sometimes you'll be told that in the key, and sometimes you won't. Sometimes you just have to figure it out in the question. So let's just get rid of that for now. The final person we're going to try and figure out is person C over here. They are unaffected, we can see, so they could either be big B, little b, or big B, big B. We can't really tell from this diagram whether or not they are either of those. We know they can be either of those because they're unaffected, but also because the parents are heterozygous. So if we do our little Punnett square, we can see that both genotypes are possible. Here and here. Like I said, they are unaffected, so they have to have 1 big B at least. But they could be either. I mean, there's a 50% chance that they're heterozygous and there's less of a chance that they're homozygous, but they could be either. So that could either be big B, little b, and the same would go for this person. These are the kids as well. If we look at child D, then has to be heterozygous because they have to have gotten the small b from their mother and then the big B they got from their dad. So let's now have a look at example 2, where we're dealing with a dominant disease, such as Huntington's disease. So let's try to figure out what person A again is. So same as before, we first write down our genetic notation. So this time, capital B is going to be for affected, aka Huntington's. Lowercase b is going to be unaffected, because unaffected is recessive, and affected or having the disease, Huntington's is dominant. So again, we have 3 possible genotypes. We have affected, which is going to be big B, little b, or big B, big B. So if they're heterozygous, they are affected, and unaffected is going to be 2 little b's, because unaffected, i.e. not having the disease, is recessive. So person A, if we have a look, is male and is unaffected, which means that their genotype has to be 2 small b's. So we can fill that in on our chart, 2 small b's. Same thing goes for anybody who's unaffected. Whether you're male or female, if you're unaffected, you have 2 small b's, the recessive allele. Now let's have a look at person B, so one of the parents. So person B is affected. They could therefore either be big B, or big B, little b. But actually, if we look at their kids, we can see that their genotype has to be big B, little b. They have to be heterozygous because of this person here. They have 2 kids that are unaffected, so they have 2 small b's, or 2 unaffected alleles, so they have to have gotten one from each of their parents. They can't just have gotten both of them from parent A. Each one of those alleles they got from each of their parents. So that means that person B who has the disease is heterozygous. So we can wipe that away and then just write big B, little b. For the same reason, these people down here are also heterozygous because they have this unaffected child. So they both have the disease, but they have an unaffected child and an affected child. The last one I guess we can figure out is their other child, person C, is also affected. So they can, in this case, either be big B, or big B, little b, and we're not sure which one. Because if we have a look at the parents, we can again do a little genetic diagram, and we can see that either possibility can happen. So you can have either 2 big B's or be heterozygous. So person C, we don't know. They're either one. So finally we're going to do 2 examples in this 3rd section where we're not told in the exam question whether disease is recessive or dominant. You have to figure it out. So this is probably the hardest part, being able to figure out if it's recessive or dominant and giving a valid reason why. So what you need to look for in this pedigree chart is where parents are different from their children. Both parents are different from their children. So we have these parents here and they have one child that has a different phenotype to them. If we look at over in the key again, we have 2 unaffected parents that have an affected child. So we then have to go through the process of trying to figure out, is it recessive or is it dominant? So say, for example, scenario 1, if the disease is recessive, would that be possible? If the disease is recessive, would it be possible for two unaffected parents to have an affected child? Let's like we normally do, assign letters. Big B is unaffected if it's recessive, and little b would be the disease or affected. Okay, so say this person here, the affected child, has got two small b's and the parents have a little b. Can they be unaffected? Well, yes, they can. If they are both carriers, if they're both heterozygous, then yes, it's possible. Let's do a little Punnett square down here just to show that it is possible. So let's say the parents are heterozygous. We do the little cross, big B, little b, little b. And we see that, yes, it's possible, and there is a 25% chance that the kid gets it. But they did get it, so in this case, yes. Now, let's see if it's possible if it were dominant. So, scenario number 2, if dominant. Okay, so if it was dominant, B would be disease, and little b would be unaffected. So if the parents are unaffected, which they are, we can see both parents are unaffected, their genotype would be two small b's. Now if we do the cross on that, and we have this, we can see that two unaffected parents, there is no way they could have an affected child. There is zero chance that that's possible. So therefore, it has to be a recessive disease. Now you'll probably figure out, because in the last example it was recessive, that this is going to be dominant. We can see that in each generation you have people that are affected, but we have to anyway go through the different scenarios anyway and give a valid reason why. Now again, in this pedigree chart, we want to have a little look at where two parents are different from a child. So here in the second and third generation, you've got parents that are different to their child. So you've got two affected parents that have an unaffected child. So again, let's have a little look at two different scenarios. Scenario 1, if dominant, would that be possible? Would it be possible for two affected parents to have an unaffected child if the disease is dominant? So so big B affected is dominant, so that's going to be disease, and little b equals unaffected. So that child would have to be two little b's, little b. They would have had to have gotten one from each parent, and if the parents were heterozygous, they could be affected but still have an unaffected child. Let's do a little Punnett square just to show that down here. I think we already know. There we go. And is it possible? Yes, it is. So the unaffected child is possible. Again, 25% chance that two people who are affected by the disease can have an unaffected child. Now let's look at the other scenario, that if this was recessive, would that be possible? So if the disease was recessive, would it be possible for two affected parents to have an unaffected child? So again, let's write out our annotation. Little b this time is affected or disease. Big B is unaffected. So the child, male child who is unaffected, well, we don't know what his genotype is, but the parents would be two little b's. And would it be possible for them to have this child here? Well, let's do the cross. We can pretty much already see that it's not possible. Let's do it anyways. And there you go. It is not possible for two parents who are affected, who have the disease, if it was recessive, to have an unaffected child. 0% chance. So just look at that in an exam where the parents are different to their child.